Hello, this is Jack Jackson. In this video, I'm going to talk a little bit about an application, that activity that I've created for GeoGebra for doing some descriptive statistics. So I've actually started to collect together a bunch of resources for probability and statistics and collected them in this one GeoGebra book. I'm trying to collect some of the best things I can find for the publicly available GeoGebra apps. And then I'm trying to create my own where I think I can improve on things or fill in the blanks for some things that are not there. GeoGebra actually has a lot of built-in resources for statistics. So I'm starting by, I'll sort of organize these by the chapters that I have in my statistics class, but I've started collecting some things for descriptive statistics. And the one I want to show you today is this descriptive statistics dot plot, box plot, and more. And so here is the application here. There's some things that talk about it right here below it. But it's best if you probably open it in the app, which you can do by clicking on these three dots up here and then say open in the app. So here is the application. Now the data that's actually in here to start with is the age at the first inauguration of all the U.S. presidents. And as of this recording, this goes through President Biden. And so you will see all of the dots here. So there's a dot for every single U.S. president. I talk about some of this data in some of my other videos, but it's not. They may not be updated through President Biden. So here's the stuff with it's updated. The data is typed in here. This is actually the order, the age and the order that the presidents served. This is George Washington, John Adams, Thomas Jefferson, and so forth, going on down, ending most recently with Biden, Trump, Obama, and so forth. Um, so it figures out some descriptive statistics here: the minimum, the maximum, the median, the first quartile, and the third quartile. Uh, you can watch some of my other videos that talk a little bit about the quartiles and exactly what these things mean. And one of the things in my earlier videos is that the quartiles, uh, well, all of this stuff has only one definition for everybody except for Q1 and Q3. And there are various definitions that are used out there. Different softwares use different definitions. I use the GeoGebra built-in function for doing these, and it turns out to be the same as the built-in function on a TI-84. And that is, you take the median of the lower half for Q1 and the median for the upper half of Q3. If you have an odd number of data points, the median of that is not counted as either part of the lower half or the upper half. And any event, those are there. These are measures of central tendency: the mean, median, and the mode. Less often used, the mid-range and mid-quartile. And these are measures of variability: the range, interquartile range, the mean absolute deviation, and the standard deviation. So anyway, we can see these here, and you can see the dot plot. Okay, and so it will create a number line here. It will automatically adjust the horizontal scale for that. So that it will hold the dots. If, for example, we sort of change George Washington there 57, help me remember that, to 157, it's going to adjust the dot plot there. Of course, he was not that old; he was 57. So let's go back to that. We can also see along with this the box plot underneath. And the box plot, what that does is a visual representation of the quartiles. So moving back to the dot plot, there's an actual dot for every single one. So 57 would be right here. That's the dot for George Washington. The 61 right here is for Adams. This is for John Adams. This is 57. That was, let's see, who was next? Jefferson, then Madison, and Monroe. So 57 for Jefferson was here, 57 for Madison here, 58 for Monroe here, and so forth. Okay, so notice when something occurs more than once, they're just stacked up. So that's a dot plot. The quartiles you can see here. So the minimum is the lowest one, which is 42. We draw the whisker out to there. We have a box and whiskers plot, sometimes this is called. So the boxes in here going from the first quartile to the third. And this is the middle half of the data. So if we go between 50.5 and 60.5, we should have half of the data right here in the middle. And it basically breaks it, these 5 numbers, this 5-number summary breaks this data into 4 parts. So 1/4, at least roughly, is right here from 42 to 50.5. Half is between 50.5 and 55. A half is from 55 to 60.5. And a half is from 60.5 all the way up to 78, which is the highest, the maximum. Minimum is the lowest value, maximum is the highest value, and so forth. So the box is the middle half. So roughly a fourth here, a fourth here, a fourth here, and a fourth here. The highest fourth is much more spread out than, say, this fourth here. One of the things we can talk about is outliers. If you take the length of this box right here, that's called the interquartile range. If you take 1.5 times that and then add it onto Q3, you get to this line here, which is called the upper fence. And if we take that length of 1.5 times the length of this box and go to the left of Q1 that far, that's where the lower fence is. Anything outside those fences is considered an outlier. So there's nothing over here, so there's no outliers on the low end. There is an outlier on the upper end. So notice when you do a box plot in GeoGebra, and there's actually a command for that. Luckily, I didn't have to build that myself. There is it's an unmodified one, so the whiskers go all the way out to the minimum and the maximum. But sometimes you'll see these as a modified box plot. Instead of this whisker going to here, you'll put a dot there or something out here at 78 for the outlier, and then the whisker will go out to the next one, biggest one that's inside the fence, which in this case would be 70 right there. So we can see that. So we see that President Biden is an outlier, exceptionally old. Centers, we can see the mean, which is right there. The mean is the balance point, the center point there. So that if we were to think of these dots as weights, this would be where we would put the fulcrum to balance that out. Okay. The median, of course, is the same. We already have talked about the median here. Half the data is below it, half the data is above it. So there it is at 55. The mode is the most often occurring one, which is at 54. It's the one with the most dots. We also have the mid-range. That's less often used. The mid-range is just averaging the highest and lowest. So 42 plus 78 divided by 2 is the mid-range. So the mid-range, it will be the same distance from the mid-range to the highest value and from the mid-range to the lowest value. And we can see that illustrated. The mid-quartile is a similar kind of thing. The mid-quartile is 55.5. The mean was 55.49, so those are extremely close to each other. So the mid-quartile is right there, and it's exactly the same distance from to the bottom of the box here down to Q1 as it is to the top of the box, which is at Q3. Notice that's a little bit to the right of the median, so we have that. The mean is to the right of the median here. And when that happens, it's slightly skewed to the right, and that's because of this outlier out here. But pretty much this is a pretty symmetric type of a graph. These are very close together. Now we can also measure some variability. First of all, we can talk about the range. The range is this distance from minimum to maximum all the way across here. It's that purple distance, 36. The interquartile range is the distance from Q1 to Q3. It's the length of the box here. These values are over here in the side, and they're also seen here. The mean absolute deviation is a little harder to explain, but what happens is on the mean absolute deviation, you find out how far each point is from the mean, take the absolute value of that difference, so data point minus the mean and then absolute value, and then you average those, add them up and divide by how many points you have. And that's the mean absolute deviation. The standard deviation is similar to the mean absolute deviation, but instead of taking the absolute value, you square them. So what we do here is basically take for the standard deviation, we take the difference in the x value minus the mean, take that difference, square it, and then average those, add them up and divide by how many you have. That would be the standard deviation if this was a population. If it's a sample, instead of dividing by the number of data points, we divide by one less than the number of data points. And I think this number is probably treated as a sample, but I'd have to verify that. So I have the links here of the mean, absolute deviation, the standard deviation sort of centered up on the mean, but we can see how they compare. The interquartile range is a little bit longer. Mean absolute deviations here, standard deviation is a little bigger, interquartile bigger. Of course, range is the biggest. But those four things are measures of variability, how far spread the data is. And so we can turn these things on and off with the check boxes there and see that. And you can experiment with this a little bit and say, well, what happens if we change a point to some of these things? How does it change some of these different values? And I'll let you experiment with that if you can get to this. This is of course um, a freely available uh, uh, GeoGebra applet that I have uploaded to GeoGebra's site, so you can search for this and find it uh, on my site there. And so there's a nice little applet that you can use to generate box plots, uh, dot plots, and also on them mark some of these other different descriptive statistics.